Three identical point charges of magnitude 16 microcoulomb are placed at the three corners of a square of side A. What are the magnitude and direction of the electric field due to the three charges of the vacant fourth corner? This is very interesting, especially when you consider the fact that one corner is vacant. So I'm just going to take one corner vacant. Now, what is interesting to note here is, okay, at this point, right, this is the point of observation. There are no charges present here. So I can straightforward find the resultant of the electric field at all those pointers. So I'm also given the side of the square as well, a. So for one of the vectors, which is probably 2, so one of the charges 2, I need to find the diagonal also. So the length of the diagonal is, since it's a right angle triangle, since the diagonal makes a right angle triangle, the value is simply a squared plus a squared, the whole square root, and so the answer is simply root 2a. So root 2a is the distance here. So this gives me two equations of electric field, E1 which is equal to E3, always giving us the same value, k into 16 microcoulomb the whole squared by a squared, while E2 will give me an answer k into 16 mu the whole squared, k into 16 mu, not the whole square again, sorry, it's just kq, a whole divided by, now the distance, remember, is root 2a, right? So root 2a the whole square. So I have now found my values of E1, E3 and E2. Now here something interesting has happened. Now for the vectors E1 and E3, right, E1 and E3 are both perpendicular to each other, hence they have both x, only either x or y components, or and then you have the E2 vector, which is in fact at an angle naturally 45 degree, because remember E1 and E3 are equal, right? So since E1 and E3 are equal, the angle between them is simply 90 degrees. It's just that it's vertically opposite because on the opposite side it's just a square. So you know for a fact that so the angle between them, the angle which made by E2 with the x-axis is 45 degree, right? So in fact, to find the resultant vector, it's very much straightforward. I can find the resultant of the vectors E1 and E3, or I can split E2 into two components and go forward with it. Both approaches are welcome. In fact, let's take the approach in which we are splitting the vector E2 into two components, but remember, since it's sine 45 degree is equal to cos 45 degree, I'll just end up having another root 2 at the bottom as well. So E2x, which I can only add with E1, and E2y, which I can add only with E2, will both have the same value, just as we expected, k into 16 mu multiplied by 2 root 2 a squared, because remember sine 45 degree is equal to cos 45 degree, which is still 1 over root 2. So that's how I'm going to get my value here, 2 root 2 multiplied by a, yeah, because I have already solved for the root as well. So that's just about it in the denominator as well. So the denominator I have 2 root a. Now I am welcome to find the resultant electric field. So what is the resultant electric field? The resultant electric field is equal to sum of all the x components plus sum of all the y components. So I can now add the x components and y components together to find my final answer. So let's now do that and find my final answer. So square root of k into 16u by a squared, right, is going to be the value of E1 plus the only x component that I can add with it is k into 16u u mu whole divided by 2 root 2a. Remember, the x components are in the same direction, so I can add them both together and then square them up, plus the same equation will again repeat on the y-axis as well. So this is simply the same equation repeated over, so I can just simplify it and express it as 2, because it's the same equation. I'm just multiplying the same equation again. So under the square root, I'm just going to put a 2 here, because I'm adding two variables that are exactly the same. So I just now have to only simplify whatever is inside here, which is k multiplied by 16 mu by 2 root 2 a, so a squared Have I lost some of the variables? No, I haven't. In fact, there is still an a square in the denominator, which I missed out. So the a squared still remains here. So in fact, I can take the k into 16 mu by a squared term outside because it's common. And that's about it. 1. So it's just going to be a 1 plus 1 over 2 root 2, or everything under a square root. Let's do that in the next page. So everything under the square root, I'm taking it out. 2 into k 2 into k into 16 into 10 to the power minus 6 whole divided by a squared. I've taken the terms out correctly, and so it's just going to be multiplied by 1 plus 1 over 2 root 2. Shall we check if the 1 plus 2 1 over 2 root 2 is correct? 1 over 2 root 2 is correct because this term will always be there, because whenever you are adding both the y component and the x component respectively to e1 and e2, because let's recap once more. Ex is equal to e1 plus e2x, and ey is equal to e2 plus e2y, and e2 does not have an x component because it's completely along the y-axis. E1 does not have a y component because it's completely along the x-axis. That's simple logic here. And here now you can just do some additional simplification, but again, since we do not have the value of a, no additional value can be reached. You are free to even leave the solution at this point of time as well, because ultimately 32 into 9 will also not get you anywhere near to removing the square root as well. You can just write down this answer at this point and move on, because the variable for the distance has not been given because it's side A. Thank you.